Let's go ahead and get started today. The first thing I want to say is, many of you caught on that there was a mistake with the first question of the quiz that was due between, Friday noon and Saturday at midnight, going into Sunday. I apologize. I'll take accountability for that. I didn't check the answers as thoroughly when they were inputted into the Brightspace. So everyone who attempted that question got a point. Sorry if that worried any of you. Next thing to remind you is homework 1 is due tonight. Make sure you get that in as soon as possible. I don't want to see any, but I couldn't get it to upload, type of things, work on this early. There's enough students in this class that if everyone rushes the system at the last minute, it's not going to work very well. And then homework 2 will be assigned today for next Monday. Additionally, there will be a quiz again this Friday leading into Saturday. We hope to get the homework graded to you before the end of this week. So, it's definitely always a challenge to get the teaching staff, raring to go this early in the semester and work out all the bugs we have with our solutions. Good question, Riyadh. Is exam 1 going to be lecture set 1 and lecture set 2? Yes. So I plan to only cover lecture set 1 and lecture set 2 content on the first exam. So, be prepared. I also am working on getting some more practice problems out for the people who asked for it. I'll look in one of my old textbooks and see if I can produce some problems that will do it. There won't be any solutions for them, but if you at least want practice problems, I will at least throw out things that, might be similar to what you see on the exam. Oh, no multiple choice in this class. Everything is a workout problem. We're going to try to, award partial credit as, much as we can. Again, remember, you're allowed to use a calculator that doesn't connect to the internet. Brandon, will the problems be posted on Brightspace? That's my intention. Any other procedural questions? If not, please speak up. I just, I won't be able to see your question otherwise. Let's go ahead and share my screen. So now you should be able to see my screen. So, after getting some feedback from students during office hours, I was able to spot some problems in the slides. So one of the first problems was in this very important, FET modes of operation table. The PMOS voltage condition for saturation mode was listed incorrectly. If you're using this absolute value approach, which it seems few of you were actually doing, you're taking more of the textbook approach, where you always use VGS and let V sub capital T lowercase h be positive or negative as you see fit. But this right here needs to be VSD is greater than or equal to VSG minus absolute value of VTP. That was a mistake from before. The next mistake I wanted to point out let's see. I have to jump quite a bit if I remember right. Slide 35. I made it explicit that the large signal pi or T models are square law equations. The basic drain current equations for saturation mode or triode mode. The next major error is later on. So on slide 54, I cleaned up a lot of the cruft that had, been left over from when I taught ECE 255. So, I don't reference any BJT terminals or BJT circuits anymore. This should just be talking about MOSFET circuits. next major change. Similarly, on slide 69, I'm using the letter pi and everything, Greek letter pi, and I removed references to terminals that aren't there anymore. Slide 74. Remarks on CS amplifiers. This one had a big one. Oh, and I didn't correct it. I have to upload it again. Darn. I have it corrected in my notes, but I forgot to correct it here. Remove the part where it says lowers GM and hence, or I guess remove GM and hence. So basically, it should read lowering RD to lower RO as a trade-off because it also lowers AV. Instead, use a CD post amplifier. I will be like, note to self, fix that again. And I think that takes us up to the new slides for today. So let's go back and review a little bit. So we're using, our models, a hybrid pi model and the equivalent T models for the FET. And, we said there's 3 basic single transistor amplifiers, common source amplifier. We covered extensively, including with source degeneration. It's got high gain and good input resistance, but the output resistance is higher than we like and the bandwidth is limited. And then we started talking about the common drain amplifier. So the common drain amplifier looks like this, where you can see the inputs between gate and ground and the outputs between the source terminal and ground. The drain terminal is connected to common, sometimes through a resistor, sometimes, through a very, very large capacitor. So in the small signal model, it appears like it's being connected to ground. We got these equations where we notice that, the overall voltage gain GV is going to be something that's, ever so slightly less than 1. So it always attenuates, never provides any gain. But all the resistances are in good shape. It's got wide bandwidth, so it's very nice to use for its input resistance and output resistance metrics, which recall are 2 out of the 3 metrics we're looking at. Now, new slide, slide 81. Discrete source follower looks something like this, where you can see we've got an input stage, which is our Thevenin equivalent voltage source and its series resistance. We'll use a coupling capacitor CC1 to get the AC part into the DC biasing circuit formed by RG, Q1, and RS. We connect the drain directly to VDD. We don't even bother with another resistor for the biasing purposes. We have RS here for biasing, and then we have RL at the output, which is our load resistance through this coupling capacitor. Do our small signal equivalent circuit, where this DC voltage source and this DC voltage source get replaced with short circuits to ground. We have no DC current sources to replace with open circuits. These large capacitances get replaced with short circuits in our mid-frequency model, as your book likes to term it. And we have no large inductances to make it into open circuits. So we get a circuit that looks a bit like this, where we see the input resistance looking to the right of where VI is defined is just going to be RG. And we see that the output resistance is going to be RS in parallel with RO in parallel with 1 over GM. However, because that's looking to the left of the load. However, we notice that RS and RO are going to be much bigger than 1 over GM, which, 1 over GM is going to be usually in the, tens of ohms, maybe 100 ohms or so, usually not very big. So it's going to be the dominant factor when put in parallel with all these larger resistances. So the output resistance is about 1 over GM. And then finally, GV is the input voltage divider of Rin, which is just Rg, over Rin plus Rsig, times, the voltage gain of the amplifier proper. So GM times Rs parallel Ro parallel RL over 1 plus the same thing. So again, you'll get an answer that's, something that's less than 1 times something only slightly less than 1. So you'll get something that's just, moderately less than 1. Any questions about why is 1 over GM in parallel with Rs and Ro rather than in series? Ooh. Let's see if I can refresh my memory real fast. I don't think I have an error. On slide 82, you get that the output resistance should definitely be the parallel combination of these two. Okay, hear me out. So because this current control current source has the same current flowing through it as the current in 1 over GM, it's like the other end of 1 over GM is connected directly to ground. So basically, you could bring this point up here below the CCCS and bring it down to ground for the purposes of calculating output resistance only. So then you'll see RO, RS, and 1 over GM all in parallel. Does that explain your? Yep. Okay. Good. Because they only share one node. I mean, yeah. I mean, like, they're not float. It's not floating, and it's sharing one node. Like, probably not the most elegant solution, or not the most elegant way of putting it, Riyadh. But like, you caught what was going on visually. I'm not calling you out. It's like, I'm just saying, perhaps, that would be a partial credit answer on an exam. I'd be like, you caught what was going on, but you're not explaining it fully. But good observation. The other major amplifier is the common gate amplifier. It's the last of our single transistor amplifiers. So here you can see the gate is tied to common in the small signal model, and the input goes into the source and out of the drain. Sometimes it's drawn in a very weird way where the transistor has the gate facing down and like the source to the left and the drain to the right. I think that's very confusing. It's just another thing that's there to throw you off, really. So you can always, redraw it in a sort of, rectilinear fashion so that you can have a single transistor in the orientation you prefer. So I prefer to draw it like this as the common gate amplifier. So here we have, our Thevenin equivalent source. VI is, this point with respect to ground, and then we'll have some drain resistance right here. We'll use the equivalent T model to analyze it. So we replace this transistor with its equivalent T model. Should be pretty clear what we did here. We left out the output resistance from the early effect because it makes things quite complicated. We covered it in my previous ECE 255 course later on, but for a first pass over how to make these sorts of amplifiers, let's not deal with the early effect. You have to deal with applying test voltage and then measuring test current to figure out all of your input and output resistances. So the input characteristics, if we look to the right of Rsig, what does the input resistance look like? Well, it looks like 1 over GM. And, we can say, okay, this is, to find the input resistance, we'll turn off our source and we'll say we have ground, Rsig, and then 1 over GM. So what is VI in terms of Vsig? Well, since it goes back to ground, this is actually just a voltage divider in a weird way where normally we would draw 1 over GM on bottom. However, it's, kind of flipped so that, it's going up instead of, going, resistor and then resistor to ground. So our lower resistor is 1 over GM. So the input characteristics is, VI is equal to V sig, 1 over GM over R sig plus 1 over GM, multiply top and bottom by GM. You get this equation right here. Output characteristics, well, if you look, here where we would normally attach a load and look to the left, again, we're not drawing the load because it makes things a little bit too cluttered for our first pass at understanding this. But looking to the left, we would see that the output resistance is just RD. And the output resistance, well, the current that flows down here is the same as the current that flows here. So we get GMVI times RD. And the voltage gain of the amplifier is a positive GMRD. Contrast that to the open circuit voltage gain of the common source amplifier, where it was, minus GM, RD in parallel of RO. So if we're neglecting RO, the common gain amplifier looks very similar, except with it's non-inverting instead of inverting. And of course, if we do attach load resistance, the voltage gain of the amplifier proper is GM RD in parallel of RL. And then lastly, we apply our input voltage divider, and we will get something that looks like this, where we sort of canceled out a GM in the numerator. So if you look at this voltage gain, it's basically saying the equivalent resistance seen in the drain over the equivalent resistance seen in the source with a positive sign is our overall voltage gain. Okay. So some remarks. So common gate amplifiers, or CGA amplifiers, have the advantage of having a moderate GV. You have to control the value of R sig you use, so you can't just attach any signal source willy-nilly to this thing. You want to keep it at least, no greater than an order of magnitude above RD. And it has nice wide bandwidth to high frequencies, which is another pro that we can't really analyze with this circuit. The disadvantage is that Rin is very low when we want it to be high, and RO is very high when we want it to be low. So it's like all the resistances are flip-flopped. They're the wrong way around for a voltage amplifier. And compared to earlier versions of the notes, I didn't have RD there. It should be RD. Common gate amplifiers are also useful as input amplifiers coming from low resistance cables for impedance matching. So when you deal with high frequency circuits, sometimes you want to match a low resistance of a cable to the low resistance at the input of your amplifier to avoid signal reflections. We won't get to signal reflections until the very last day of this course. But, keep in mind that, there are cases where we do want the low input resistance, generally in high frequency applications. If you don't get the gain you want out of a common gate amplifier, follow it with the common source amplifier for the required gain. So you make a multi-stage amplifier that way. Lowering RD to lower RO, the output resistance is basically just RD, is a trade-off because it also, this one should also be corrected. It doesn't lower GM. So I'm going to cross out GM and hence, because it also lowers AV even more. Instead, uses common drain post amplifier. So, because the common drain amplifier has the correct input and output resistance characteristics. So yeah, get rid of GM and hence in your notes. Just when I think I get rid of all the errors. Saying things out loud helps me find more errors. Questions to this point? Hearing no questions, we'll move on. So, Common gate amplifiers have the advantage of a I just read this. So here's like if we were to combine the DC biasing network with all of the AC things we want. So we want our AC signal source, a load resistance, and then here's a very simple 2 resistor biasing network using 2 supplies where we can ground the gate. So we'll have VDD be a positive supply, VSS be a negative supply. And we'll sort of keep to that convention. RS in the source, RD in the drain, and then 2 coupling capacitors, CC1 and CC2. So if we take the small signal equivalent circuit, again, replace our DC voltage sources with short circuits to ground, and replace our very large coupling capacitors with short circuits, and use our equivalent T model for the transistor itself, and we get this sort of circuit configuration, where I see another mistake. Instead of RD here, that should be RS. Oh man, I'm batting 1,000. Yeah, that should be RS. Okay. But you can kind of, hopefully you've been thinking about small signal equivalent circuits, and you can think about how you would form them. So the input resistance is 1 over GM in parallel with RS. Remember, this is RS. Notice, we look into this terminal and we see, 2 resistors that each lead off to ground. That input resistance, because 1 over GM is so much smaller than RS, is going to be about 1 over GM. We have this input voltage divider where we have V sig times Rin over Rn plus R sig is going to be this voltage right here, Vi, the input to our amplifier. The output resistance looking to the left of the load is Rd. VO is GMVI times Rd in parallel with RL. And then lastly, we get the overall voltage gain, GM, Rn over Rn plus R sig, Rd in parallel with RL. Now, we went through a lot. We went through the 3 metrics. We also went through like open circuit voltage gain as well as voltage gain of the amplifier proper on the way to driving overall voltage gain. Keeping all these things straight can be a lot of work. However, this is where we have this handy table. So, not considering the biasing network and just considering, the load resistance and the drain resistance where applicable. Here is, and also neglecting the early effects. So like there's like 3 levels of simplification that go on in this table. Here is, a nice summary table of MOSFET amplifiers. So we got the common source amplifier, the common source amplifier with source degeneration. In other words, there's the presence of R sub little s, the common gate amplifier, and the common drain amplifier, also known as the source follower. These figure numbers don't make any sense to you because you don't have the Sedgwick Smith textbook, most likely. And then, of course, we have all the relevant equations. And you can see, for example, you get negative gain from a common source amplifier, a positive gain with a common gate amplifier, and a gain that's positive but slightly less than 1 for the source follower. Most of the input resistances are infinite except for the common gate because it doesn't look into the gate, it looks into the source where it sees 1 over GM from our equivalent T model. And then most of the output resistances are just, the drain resistance, sometimes when we consider the early effect, we can throw in a little R sub O in there. And then the exception, of course, be the source follower, where our output looks into the source where you see 1 over GM. Hopefully, you can start noticing these patterns of where resistances from the drain appear, where resistances in the source appear in these equations. Oh, never mind. Okay, AJ. This is microelectronics. Circuits by Cedra and Smith, 7th edition. I have a copy in my office in case you want to use it, Alice, or anyone else, really. You can look at it and maybe get a little bit more perspective on how these circuits. Y'all find it online. Don't violate copyright, but also I'm not looking. You can get the tables for free from the website even if you don't own the book. I know that much. So, and yeah, so if you wondered why I have most of this first lecture prepared already, or excuse me, the first lecture set prepared already, it's because I used the exact same material when I taught ECE 255. So, but that class doesn't exist anymore, so now it's part of ECE 20002. Some remarks on the single transistor amplifiers. So FET amplifiers have infinite RN, except for the common gate amplifier, and are simpler to analyze than their equivalent BJT amplifiers. Even though discrete circuit amplifiers on PCBs, printed circuit boards, that is, are typically built with bipolar junction transistors, we use MOSFETs just like you would for an integrated circuit amplifier, because that's all we study in this course. Again, it's really hard to find small signal MOSFETs that you can just buy, just one MOSFET. That's hard to find nowadays. But this is how you would build them as discrete circuits. That's why the word discrete appears on top of slides like slide 85. Some on the 3 single transistor amplifier types use the common source amplifier, multiple if needed, for the bulk of gain in a multi-stage amplifier. Use source degeneration to improve performance at the expense of gain in that stage. Again, it improves R out, it improves bandwidth, but you just lose some of your gain. But that's okay because you can make it up with multiple stages of common source amplifier. Use the common gate amplifier as the input stage in high frequency applications. We don't get a chance to talk about it in this course, but there's also something called a cascode amplifier. Yes, cascode, where you use the common gate amplifier as a current buffer, just like the common drain amplifier is a voltage buffer and a good output stage in high power amplifiers. So lastly, next to last, the finite output resistance, RO, in the small signal amplifiers from the early effect was included only where it's mathematically convenient. CS amplifiers by reducing gain only by about 10%, which is another way of saying you can neglect it most of the time because, having only 10% error with some of these calculations is considered pretty good and pretty thorough. The common drain amplifier, it reduces the open circuit voltage gain to slightly less than 1 instead of being exactly 1 mathematically. And then lastly, again, it's to our deficit that we don't get a chance to cover this, but SPICE analysis shows that we get very similar results when RO is neglected for discrete circuit amplifiers. You should always consider the output resistance when analyzing, integrated circuit amplifiers, ones that you would build in a chip itself. Not covering SPICE, kind of sucks, but we just don't have time. A discrete circuit is one that you would build on a circuit board or on, proto board or a printed circuit board by saying, I buy a part called a resistor and I attach it to a part called a capacitor and to a part called a MOSFET, and then I, have paths for the current to flow between them. Versus an integrated circuit where I am fabricating layers of silicon to make the transistor, and I can make it how I want, and I can put it next to other resistors which are fabricated, in silicon or with, maybe carbon film or something like that. And then I make a capacitor by literally, putting, a plate of copper above a plate of copper, where, there is a capacitance and resistance associated with those types of things, but it's not like I'm buying a physical part called a resistor or a capacitor. Does that make sense, Siad? Yes. Any other questions? about our single transistor amplifiers. These are good to know. In practice, you wouldn't go out and be like, oh, I need an amplifier. I should use the common gate amplifier for this application. You would just go and say, I need a, low input impedance, amplifier, buy it from TI or Maxim or any of the other major NXP, any of the other major chip fabs, and be like, oh, this amplifier serves my purpose. You would rarely build these things as a first resort method. It's only when you really need to control your parameters or you really know what you're doing that you go about this process. But these are good to know because they are the basis. What does a buffer do again? Buffer basically means make a copy of the input at the output. So a voltage buffer says make a copy of the input voltage at the output. So the voltage buffer made from op amps and the common drain amplifier do something very similar, where it basically copies the same input and waveform at the output, just slightly smaller. And a current buffer basically says, hey, I need a copy of the current you put into this device at the output. Relatively unattenuated. Does that answer your question, Pranav? You're welcome. So, again, you would rarely buy these things, but, if you're trying to understand what goes on inside of these, IC amplifiers, they're all made from, one or two transistor amplifiers, single or double transistor amplifiers. And, they're commercial, they cascade multiple of these building blocks together. So if you want to understand the data sheet, which you should want to whenever you're using a part, and understand the block diagram of how things work together, it's helpful to understand how all these work. In my ECE 255 class, this was like the penultimate step of the course, which was like trying to understand multi-stage amplifiers. This was supposed to be the very fun stuff. This was part of the course motivation for that course, is understanding how the op amp works. And here we're like, by the 7th lecture, you should understand what took me, 40 lectures to get to, basically. And even then, I didn't really do it justice. So take that for what you will for the philosophy of ECE 20002. So in each of the amplifier stages, they each serve a specific purpose. So for the input stage, you want a very high input resistance. You see, we had stages that had infinite input resistance, so we should be able to achieve that easily. A large common mode rejection ratio, or CMRR, we'll define that on the next slide, and then a modest differential gain to get things going. All the middle stages will provide the bulk of the voltage gain. It'll somehow convert the differential signal, where you take the input as a difference between two things, and then you output as two different lines where you're supposed to take the difference between them. And then differential single-ended means it takes, two, or I guess from your perspective, it'll take two signals going in, and then you have your amplifier, and then spits out just a single line where the voltage with respect to ground is our output. It also does DC level shifting. So that means, you're going to alternate between PMOS and NMOS so that you can swing both positive and negative. And then we'll have an output stage with low output resistance, and it needs to be very efficient to minimize power dissipation, because after all this voltage gain, any sort of internal resistance in the output stage will cause huge amounts of power dissipation, which means, big heat sinks, getting very hot, things you want to avoid as an electrical engineer. Because remember, it's better to leave the thermodynamics to the mechanical engineers. So that's why we want to be efficient. We will handle basic op-amp configuration in a very condensed manner. So we'll get through that because it's what your book does. And if you're taking the ECE 20008 lab, or maybe even the 20,000, I think it's the 20008 lab, you will build this amplifier yourself. And finally, even though we said that the common drain amplifier was a good output stage, if you study output stages in particular, the so-called Class A amplifier, the traditional source amplifier, is limited to 25% efficiency as the theoretical maximum, and it lacks any sort of short circuit protection that you would want. So even though we're going to use the common drain amplifiers or output stage, in practice, the study of output stages would be, its own lecture, basically. I don't know what Riyadh said was cool, but I'm pretty sure it's cool. So I relabeled this slide from what might be in the earlier versions of the note. So MOS common mode rejection ratio. No real-world amplifier can perfectly ignore voltage in common with two inputs. So say, for example, we have, an input A at 5 volts and input, B at, 3 volts. The difference between them should be 2 volts. And, we should only amplify the 2 volts going from input to output. However, both of them have 4 volts in common with each other. It's just 4 plus 1 minus 1 for, inputs A and B. And that common mode voltage is amplified by all real world amplifiers. So if you want to define it, differential mode voltage be VN minus V minus. So for my 5 volts and 3 volts example, VID was 2 volts, and the common mode input voltage was 1/2 of 5 plus 3, or 4 volts. It's literally the average of the two voltages. So the total output will be the output voltage is the differential gain AD times the differential voltage at the input VID, plus ACM, the common mode gain, times VICM, the common mode input voltage, where we expect AD to be much, 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 much bigger than ACM. So again, we're dealing with, ideally an infinite differential gain and 0 common mode gain. In practice, we're dealing with differential gain that might be like 10,000 and a common mode gain that might be, I don't know, 7. So, there's, at least 3 orders of magnitude difference going on there. So the common mode rejection ratio, or CMRR, shows how good a differential pair or any sort of differential amplifier that takes, 2 inputs and then spits out an output or a pair of outputs, amplifies the differential mode or DM signals while rejecting the CM noise. Because most of the time, the common mode isn't your intentional pathway. It's where noise couples onto, it's interference from other things, it's, the presence of a radio station a few blocks away. All these sorts of bad things couple equally onto wires, and we call it common mode noise usually. This was like the subject of my master's thesis, so I got to really restrain myself from ranting for a very long time about it. So CMRR is typically reported in decibels. So CMRR in decibels is just 20 times the log of the absolute value of CMRR, where you could say CMRR itself is just the absolute value of differential gain over absolute value of common mode gain. So that's just a definition. You might get a problem or two on it, but we're not really going to work too much with it because we didn't cover differential amplifiers in any detail, because you can build them with MOSFETs, but we're just going to jump right into this 3-stage MOSFET op amp. So I'm going to read from slide 92 while keeping slide 91 up. So, this is a little intimidating. There's 9 different MOSFETs here. And, by the time you get to 4 MOSFET circuits, analyzing them explicitly using the saturation mode equation and current transfer ratios and things like that, and, taking account the early effect, gets a little out of control. And here we have 9 MOSFETs. So it's not something you would want to analyze you know, as like, a single circuit. However, we understand what some of these circuit blocks do. So as a little bit of preface, this is a discrete three-stage op-amp from, I think, ECE 2K or 2008, except I think I inverted the polarity. So all of the P-channel MOSFETs used N-channel MOSFETs, and all of the N-channel MOSFETs used P-channel MOSFETs instead. So I'm just showing you my version of it because, one, I have this from the Cedra and Smith textbook. Well, I drew it from the Cedra and Smith textbook as inspiration. And two, showing you a different version of the same circuit can only be to your benefit. So let's talk about what's going on here. So it takes the popular two-stage MOSFET configuration of Q1 through Q8, and then it appends or by cascading a source follower. So most of the time you would build this inside an integrated circuit. However, Sutton Hathorn decided, hey, it'd be great if you would actually build this on a PC, on a breadboard for a lab instead. Good job, Sutton. So here's the identifiable blocks. So we take this reference current, and remember, we want to do some current steering by replicating this at various places throughout the integrated circuit. So we'll have Q8 and Q5 be a current mirror, where you see that Q8 is diode connected and Q5 is a normally connected transistor. There's no connection at this point right above where the current is labeled. This is for the purpose of biasing, when we have to choose the aspect ratio of Q5 very carefully. We have this, Q1 and Q2 form what's called a differential amplifier. It is our input stage for differential gain. So it takes in an input and then it spits out an output, on both of the drains of this of Q1 and Q2. Didn't really have time to talk about it, but basically, it amplifies a difference in signals, just like the differential amplifier we showed like back on slide 9. Q3 and Q4 are a NMOS mirror. So it's another current mirror where Q3 is diode connected, Q4 is regularly connected. So this is a current mirror loaded differential amplifier, which if you study differential amplifiers, you'll learn, it solves a lot of the problems you have with current mirrors by allowing you, or with differential amplifiers, by preserving the amount of gain you get. Q8 and Q7 is another differential pair. Well, see, Q8 is regularly connected, Q7 shares the gate and is regularly connected. So this provides an active load for the second stage of the amplifier, where the second stage is this NMOS transistor Q6, where it's a common source amplifier. You see the source is connected to a supply, the input goes into the gate, and the output is taken at the drain. So being NMOS when Q1 and Q2 were PMOS means that it does level shifting. So it kind of folds things back so that we can swing a signal both positive and negative. If you had all PMOS or all NMOS, you wouldn't be able to have positive and negative signal swing in your overall amplifier. We have CC, which connects to the drains of Q2 and Q6. This is a negative feedback capacitor that does frequency compensation, which is way too complicated to talk about in the span of a single lecture. And then lastly, we take an input at the gate and then take an output at the source. So Q9 is a common drain amplifier. It's an output stage for current gain, where we've used a discrete resistor like you did in your lab, when otherwise you can see we're able to avoid using any sort of discrete resistors by using active loads such as current mirrors to bias and load the different stages. And then, here's your output voltage compared to your 2 input voltage. So this is basically your op amp, where you have inverting input into the gate of Q1 and non-inverting input into the gate of Q2, and then the output the pointy end of the triangle being the source of Q9. And this is mostly here as a survey topic. Like, we'll ask you to identify the types of transistors. We'll ask you to say what type of amplifier things are, what's a current mirror, what's the differential amplifier. Give you a hint, the differential amplifier is 2 inputs. And like normally we draw it with the gates facing out versus the current mirror where we draw it with the gates facing in. But also remember the current mirror also has to have a diode connected transistor, where drain and source, or excuse me, where drain and gate are tied together. Those are the types of questions we would ask from, this op-amp construction chapter 7 material. I had a little bit of leftover stuff from ECE 255 to talk about this. So if we wanted to do the voltage gain by stage, we could do that. So we can say the first stage with a differential amplifier, you work it out and you'll get that it's negative GM1 RO2 in parallel of RO4. Because this differential amplifier, you can see that the sources are shared together and they connect to the current mirror that's biasing this configuration. So because it's biasing this configuration, input goes into the gate, output is taken at the drain. This is a common source amplifier. So we expect negative gain, like negative GM1, and then RO2 and RO4s, or Q2 and Q4's output resistances in parallel. Similarly, the second stage is a common source amplifier. So we expect our Q6s and Q7s output resistances in parallel. And then lastly, we have a common source amplifier. So we expect, from our equations, GM9 R source in parallel of RO9, 1 plus GM9 R source in parallel of RO9. This is a common drain amplifier or the source follower. How do you find the overall gain? Remember, each of these are ratios. So it's, this is V out over V in 3. This is, V out 2 over V in 2. This is V out 1 over V in. Notice that the input of 2 is the same as the output of 1. The input of 3 is the same as the output of 2. So if you multiply them all together, all your ratios would cancel out the middle terms. You get that cross cancellation going on. So you could just multiply gains together to get your overall gain in a multi-stage amplifier. So you just multiply these together and you get positive all of these MOSFET transconductances, all of these, parallel resistances over 1 plus GM9, that parallel resistance. And, we want to keep our source to a manageable level so that we're not robbing too much gain. We don't want to make it, way too big or way too small. It's got to be manageable. Whereas, otherwise it starts to play an effect in the circuit more than we would desire. So there is something called an input offset voltage. This is more trivia than anything that I would know how to test in any depth. So you get an input offset voltage where if you apply 0 voltage at the input, make VI plus and VI minus, shorted together so that there's 0 voltage between them, you would still get an output at VO, even though mathematically you expect 0. So maybe you would modify this equation where the output voltage is, the common mode gain times the common mode input plus the differential gain plus the differential input plus an input offset voltage VOS. Now, if you have mismatched components where, these transistors aren't all identical to each other in terms of, their transconductance or aspect ratios or things like that, that's one type of random offset. But that's different from predictable quantities where even if you had perfectly matched transistors, you would have, some offset voltage introduced, from systematic reasons, systematic offset. And if you churn through a bunch of equations to make sure that, all the diode connected things don't produce different voltages at their drains compared to the regularly connected transistors, you get that you must have the aspect ratio of transistor 6 to the aspect ratio of transistor 4 must be twice that of aspect ratio of transistor 7 to that of transistor 5. Wow, that's like a big mouthful to say, but your ratio of aspect ratios must be in a type of proportion to each other. Questions? That does it for lecture set 1. If you don't have any questions about this, does anyone have a question from the homework they would like me to help them with and they think would be good for the class? I've had to remind a lot of people how like KCL, KVL works, remind the difference between mesh analysis and loop analysis. Okay. First of all, from Aubrey, explain what differential gain is again. So differential gain, as is seen on slide 90, is the gain that happens, between output and input when you have two, opposite voltages. So like plus 3 volts, minus 3 volts, plus 1 volt, minus 1 volt. So, symmetric about 0, that is the gain that would result because there'd be 0 common mode voltage. So it's a pure, equal and opposite type of gain where, you would have, the difference between those two voltages amplified. Contrast that with common mode gain, where, for example, if I were to apply 2 at the same voltage, like 1 volt and 1 volt, or, minus 3 volts and minus 3 volts, you would still get an output, but that's due only to the common mode gain because those two voltages only have things in common with each other. There's absolutely no difference between them. One will practice exams for exam 1 be released, hopefully by this Friday, along with your equation sheet. Thanks, Suraj. Question 5 kind of confused me since it seems like the voltages don't make sense with the current source factored in. I'll come back to that one, Garrett. AJ, reiterate types of questions you can expect to see on multi-stage MOSFET op amps. We'll need to calculate those aspect ratio relationships. The answer to that one is no. Or do you need to know which ones are current current mirrors, diff amps, common source, common amp, or common drain, common gate? Yeah, those are what you kind of need to know. You might, for example, say, how many depletion type MOSFETs are here? How many P-channel MOSFETs are here? How many JFETs are here? Ooh, tricky question. Forbidden knowledge. I'm trying to think what else has been asked in the past. Or we might say, okay, given the circuit, analyze this part in isolation. So, what gain expression do you expect from, Q6's contribution to the circuit? Hopefully that helps you, AJ. Okay, I will stop sharing for a little bit, and then I'll get to Garrett's question about question 5 on the homework. So question 5 on the homework. If I remember right, there's a PMOS transistor, and then there's a current source, and then the gate is connected below a resistance in the drain. So for that one, what you need to do is come up with multiple relations. So you should recognize that the gate voltage is one of the named voltages in the circuit. The source voltage is tied to a voltage source, so 10 volts in this case. The current relationship between for a MOSFET in saturation mode and triode mode. You got to figure out which mode of operation you're in, and you should be able to do KCL on VX to figure out how I splits itself between the two paths presented to it. And if you remember that the, current into a gate is 0, should make it a little more obvious how to do problem number 5. So with 2 equations, you should be able to solve problem 5. Garrett. Any other questions about anything covered in the course so far? Otherwise, I'm going to keep lecturing. Okay, I'm going to keep lecturing. So the next thing that'll be part of your first exam is lecture set 2 on ordinary differential equations for circuits, also known as ODEs. ODEs being the main topic that you would take in a class like Math 266 or Math 366, and also part of Math 262 if you're one of those people that took combined differential equations in linear algebra. So this covers chapters 8 through 12 in Talavich and Turlep's, textbook that I recommend. So for this material, we're going to cover 7 different things, or no, 5 different things. I lied, only 5. We'll talk about solutions to ordinary differential equations, some basics, the homogeneous solution, particular solution, and complete solution, which is complete solution being the sum of homogeneous and particular solutions. We'll talk about first order circuits, so RC, resistor capacitor, and RL, resistor inductor circuits, our first order circuits. We'll talk about the basic second order circuit, the LC circuit, or the tank circuit, its homogeneous solution and complete solution. And then sort of the bringing it together are LC circuits, resistor, inductor, capacitor circuits, where you have all 3 circuit elements present, also a second order circuit. And then lastly, we got to talk about how do we handle ordinary differential equations when you're dealing with switch circuits. So this is like the rawest, most complete way of dealing with circuit math. 262 is a pain. Not recommended for electrical engineers. So why study ordinary differential equations now? I'll give you the motivation. So an ordinary differential equation, ODE for short, we're going to say that phrase a lot, so I'm going to use ODE a lot, relates a combination of derivatives of a single function in one variable to a different function. So for example, you might have, some coefficient times the second derivative of x with respect to t, plus a coefficient times the first derivative of x with respect to t, plus a coefficient times x with respect to t, equals to some other function of time. These are the types of ordinary differential equations we'll deal with. They get a lot more complicated than that, but it turns out in circuits, we only need to deal with a relatively limited amount of case. So practically all of engineering, and especially electrical engineering, uses ODEs to model real-world systems. So in electrical engineering land, we use them for linear circuits, electromagnetics, control systems and electromechanical systems, signal processing. So, several, of the, 4 out of the 7, huge research areas in electrical engineering are heavily grounded in ODEs, and the other 3 definitely still use them. Thankfully, much can be understood by looking only at the constant coefficient linear differential equations. And we're like, oh, those are 2 nice special cases. Constant coefficient means that the coefficients of the derivatives of the function on the left-hand side of the ODE are not themselves function of time. So, we have coefficients that aren't functions of time. They are just literally numbers that appear. Linear means that no powers of products of the derivatives powers. That should be probably powers or products of the derivatives of the function appear. So we never see, for example, the first derivative of x times x itself. We never see, x of t squared appear in our ODE. In these definitions, the function itself is the zeroth derivative. So, yeah, this applies to the coefficient of x of t as well as, you can't multiply x of t by anything else or take x of t to the third power, so on and so forth. So it's important to know these things because you want the sort of background to understand how physical phenomena behave. Any physics-based thing, you almost always have an ODE associated with it. It's how we do our simulations. It's how we do a number of things. That being said, there are faster ways to solve things than using ordinary differential equations, and we'll progressively go through all of them: ODE methods, convolution methods, and linear or Laplace transform methods. We got to have this background out of the way so that we can understand why convolution and Laplace transforms work. And with that being said, we have reached the end of the time for today's lecture. Any further questions? If not, make sure you get your homework in before midnight tonight. I will see some of you in office hours. Goodbye. You're welcome, everyone. No need to call me sir. Goodbye.